Why do we remember the past but not the future? Why does a broken egg never unbreak? These everyday mysteries point to a deeper law of the universe. Entropy. Entropy isn't just disorder, it's about how energy spreads out and becomes less useful over time. It's the reason perpetual motion machines are impossible, and why every process, from burning stars to thinking brains, has a cost. Imagine watching a movie and reverse shattered glass reassembles. People leap out of pools dry. It looks absurd, because it defies the arrow of time, our built-in sense of entropy. The universe is a one-way street, and entropy is the signpost. Entropy explains why yesterday is different from tomorrow. To understand it, we'll travel back to the age of steam engines, where the quest for efficiency revealed a fundamental law of nature. Entropy isn't just about decay, it's also about creation. It's why life can exist, why weather happens, and why our civilization thrives. Entropy drives the story of the cosmos, from the smallest particles to the fate of the universe. Understanding entropy is like finding a secret key to how everything works. So, let's unlock the universe's most profound law. The journey starts with a simple question: how do we build a better engine? And ends with the ultimate fate of everything. The sun gives us more than just energy. It gives us high-quality, low-entropy energy. Earth receives concentrated, organized energy in the form of visible light. This is like getting a crisp $100 bill, useful and easy to spend. Earth radiates the same amount of energy back into space, but as disorganized, low-quality infrared heat, like getting your money back in a bag of pennies. The difference in energy quality is what powers life, weather, and civilization. Plants use the sun's organized light to build complex structures. Winds and ocean currents arise from uneven heating. We harness this flow to power our world. Life and complexity are possible because we ride the wave from low entropy to high entropy. The sun's energy is our cosmic allowance. Without this flow, Earth would be a dull, lifeless equilibrium. It's not just about how much energy we get, but the form it comes in. The sun's gift is order, and we spend it to create everything we see. Entropy is the price we pay for life's complexity. The story of entropy begins with the steam engine, the powerhouse of the Industrial Revolution. Engineers wanted to make engines more efficient, but a young Frenchman, Sadi Carnot, realized the key wasn't just better design, it was understanding the flow of heat. Carnot imagined an ideal engine, and discovered that work is only possible when heat flows from hot to cold. Like a water wheel needs a height difference, an engine needs a temperature difference. The bigger the difference, the more work you can get. Carnot's insight laid the foundation for thermodynamics. He showed there's a fundamental limit to efficiency. You can never turn all heat into work. Some energy always escapes as waste heat. This lost energy isn't gone. It's just spread out, less useful. Later scientists called this inevitable spreading entropy. The quest to build a better engine revealed a universal law. Every process has a cost, and that cost is paid in entropy. The second law of thermodynamics was born from the steam and sweat of industry. It's a law that shapes everything, from engines to the universe itself. And it all started with a simple question: how do we make machines better? Imagine Carnot's perfect engine, a thought experiment, not a real machine. It takes in heat from a hot source, does work, then dumps waste heat into a cold sink. Even in this ideal cycle, you can't convert all the heat into work. Some energy must always be discarded to complete the cycle. The work you get is the difference between heat in and heat out. This unavoidable waste is the heart of the second law of thermodynamics. Energy is always conserved, but its usefulness always decreases. The dumped heat is high entropy energy, spread out, less able to do work. Every engine, every process, increases the total entropy of the system and its surroundings. The universe becomes a little more uniform with every cycle. Perfect efficiency is a myth. Entropy is the price of doing anything. The second law is unbreakable, no matter how clever our machines. Entropy isn't just disorder, it's about energy spreading out. Nature moves from concentrated energy to dispersed energy. Touch a hot bar to a cold one. Heat flows, both become lukewarm, energy spreads. The system's entropy increases, you'll never see the reverse. Drop ink in water. It spreads until uniform, reaching maximum entropy. Air in a room fills every space, energy evenly distributed, a high entropy state. This is all about probability. There are far more ways for energy to be spread out than concentrated. Like a Rubik's Cube, only one solved state, but countless scrambled ones. The universe doesn't want disorder, it just follows the most probable path. Entropy is the measure of how energy disperses, not just how messy things look. The spreading out of energy is inevitable. That's why time moves forward and why order dissolves into chaos. Entropy is the universe's way of following the odds, and those odds always favor spreading out. The second law of thermodynamics says entropy always increases in an isolated system. It's why heat flows from hot to cold, why things mix, and why energy becomes less useful over time. Burn a log, its energy becomes dispersed heat, no longer useful for work. Perpetual motion machines are impossible because you can't turn all heat into work without a temperature difference. The universe demands a waste product. Entropy must increase. This law explains why buildings crumble, mountains erode, and stars burn out. It might sound bleak, but it's also why complexity can arise. Pockets of order, like life, exist because the universe as a whole moves toward higher entropy. We are temporary islands of order in a sea of increasing disorder. The second law is the ultimate reason for change, decay, and even creation. Entropy is both the destroyer and the enabler of complexity. It's the law that shapes the fate of everything, and it's never been broken. If entropy always increases, how does life exist? The answer: Earth isn't isolated. Life takes in low entropy energy, like food or sunlight, and dumps high entropy waste heat. For every bit of order we create, we increase the universe's entropy even more. Your air conditioner cools your room by pumping heat outside, but the total entropy rises. Complexity, forests, cities, brains, doesn't violate the second law. It's a consequence of it. We are temporary patterns, paid for by a massive increase in overall entropy. The sun provides low entropy energy. Space is our waste dump. Life is a brief, beautiful structure riding the cosmic flow from order to disorder. Entropy allows for pockets of order, but always at a greater cost. We exist because the universe is moving toward higher entropy. That's the paradoxical gift of the second law. The second law applies to the entire universe. At the Big Bang, the universe was hot, dense, and low entropy. Energy concentrated in a tiny point. As the universe expanded, entropy rose. Gravity pulled matter into galaxies and stars, creating order locally, but increasing entropy overall. Every star is an entropy engine, turning fuel into high-entropy light and heat. The formation of structure actually speeds up the universe's journey toward disorder. Where does this lead? The heat death. A future where all stars burn out, matter decays, and only cold, diffuse radiation remains. Maximum entropy means no temperature differences, no work, no change. Time itself loses meaning in this final equilibrium. The universe's story is one of increasing entropy, from order to uniformity. The arrow of time points to a cold, dark, and empty future. But along the way, it creates everything we know. Entropy is the universe's one-way street. Black holes are the densest objects in the universe, and for a while physicists thought they might break the second law. Throw something in, a cup of coffee, a star, and its entropy seems to vanish. But Stephen Hawking and Jacob Bekenstein showed black holes have enormous entropy, proportional to their surface area. When you add something, the black hole's entropy increases even more than what you threw in. The second law survives. Hawking discovered black holes slowly radiate energy. Hawking radiation, eventually evaporating completely. This radiation is pure, high entropy energy. Black holes aren't eternal prisons, they're ultimate entropy machines. They take in order and over eons return it as the most disordered energy possible. In their final moments, they explode in a flash of entropy. Black holes are the universe's last, most efficient processors of order into chaos. Even at the edge of physics, entropy rules. Entropy can seem bleak, a law of decay and loss, but it's also the engine of creation. Without the flow from low to high entropy, the universe would be static and lifeless. The dance between gravity's order and entropy's spread gives us galaxies, stars, and life. We are fleeting patterns, surfing the wave of increasing entropy. Life, thought, and beauty are temporary, paid for by the universe's march toward disorder. Every broken egg, every cooling cup, is the law of change at work. Entropy makes the universe a dynamic story, not a static picture. It's the source of all impermanent beauty, including us. The second law is not just an end, but the reason for every beginning, and that's a wonder worth celebrating.